Hi everyone, so welcome to the session. First of all, this is an interesting question. This is a PNC chessboard puzzle, a very popular one. Before I start solving, give you some anecdote, I'll read out the question, I'll tell you what exactly is going on in my mind and why have I even designed this question in the first place. So the first thing first, we are about to start pre-recorded videos for, you will see the snippets of them, pre-recorded session for the higher maths part. Permutation combination is the first area that usually I deal when I talk about higher maths or modern maths. Okay, having said that, there is a methodical way through which I'm proceeding with these lectures, set theory and then PNC. But then the idea is that there are going to be fair bit inclusion of puzzles just to make sure that the students who are going to utilize these course will invoke some thinking, some lateral thinking. There is no one set method, there is no one set standard method that is the greatest. Ideally, a student who wants to excel at the area of permutation combination should go in steps. They should always understand that this is uh, a particular method that I understand. There could be another method that is completely out of the box for me. It may not have to be the optimal way, but there are other methods. The topic itself is called arrangements and selection. So permutation is basically another pristine term for arrangements, right? Having said that, let's look into this question. In this question, we are given that how many, okay, hold on. Let me take the pen. Just give me 1 second. Yeah. So how many ways can two squares be selected on a chessboard such that the selected squares have exactly one vertex in common? So first of all, we need to appreciate the fact what exactly is a vertex. I hope all of us are aware of a vertex. So a vertex is typically when I take a square, okay, something like this. In this square, these are the vertices. Okay, the vertex you can call the vertices. Vertex is the singular term and vertices is the plural form. Okay, so these are your vertices. Edges are these lines, that the lines that connect the vertices are the edges. And then there is the interior part, which you can call the interior of the square, interior of the cube, depending upon what sort of a figure you have. So first of all, let's take the terms out of the picture. Okay, now let's focus on the fact that what is it given. So I will replicate it for the entire chessboard, don't worry. I'm just going to give you the highlight here. So they're asking us for two squares such that the selected squares have exactly one vertex. So suppose I choose this square and I choose this square. They have exactly one vertex in common. Is there any other way through which I can choose between the not these diagonal ones so that they have one more vertex in common? Is there any other way? In this figure there is no possibility, but if I look into these two squares, there is a possibility these two square also have a, let's say, common vertex, just one common vertex, because we need to calculate for exactly one common vertex that is given in the question, right? So the idea is that when I replicate it into a square kind of a picture, wherein I know for a fact that some more elements will get added, you will realize that this is the first. So hold on, this is the difficult part, right? When I have to make you visualize the figure, that is the most difficult part. So when I'm looking at this one, so the pink 2 by 2, I'll call it the 2 by 2, first 2 by 2. I'm not going to call it the bigger square and smaller square. I'll call it the big 2 by 2. In the big 2 by 2, obviously I have this one and this one that has one vertex, exactly one vertex common. Obviously this is another one and this is another one. So there are two such pair of squares that have exactly one vertex common. When I replicate the same figure to the next, for example, when I'm looking at this square, now the problem is that this thing and this thing also is will have a common vertex or exactly one common vertex. The problem, however, is that this will already have been calculated in the first square itself. Okay, so let me use a different color perhaps. Hold on, let me see if I can use this color. Yeah, so just to eliminate double counting, or not have double counting in picture, I will just take these squares and then I'll try to predict it for the entire picture. Having given you the idea, now let me take you to the, let's say, chess board simulation. So this is some simulation which I have designed, and mota mota it will do our job. Okay, first of all, the same idea. Okay, so we will first of all we'll just work around the same idea that I have given you. That idea is pretty sacrosanct in its entirety, so we'll just be focusing on the first 2 by 2. So this is the first 2 by 2. In this 2 by 2, if you see, these are the two squares that are, I'm taking them. Let's say I'm taking another square, this one, and this is the one. In that ways, you can see that I'm eliminating the scope for the squares to have double counting in picture. Okay, so how many 2 by 2s can I fit in this belt? How many 2 by 2s can I fit in this belt? This, you can call it a belt, you can visualize it as a belt. Okay, so if you pay attention, there are exactly going to be 7 2 by 2s. I'll write it. So this is not 7 raised to the power 2 by 2, please pay attention. This is 7 2 by 2s, okay, in the, let's say, this direction. Once I have designed this thing, I can also go in the, in the column wise vertical direction. For example, I can also go down like this. In that case, I'll get this one. And similarly, if I take another square, let's say I use this color. So if I take this 2 by 2, I can also take these things common. Okay, and if you see, there aren't going to be any commonality. Obviously, you'll have to sit and you'll have to check. But then I'm telling you, I'm giving you the idea, that's why. So how many squares? And by now I am pretty sure you're very much confirmed that there are going to be 7 2 by 2s that will have how many squares? So the first square has 2 squares. The first 2 by 2 has 2 squares that have exactly one common vertex. Okay, and we have replicated that to 7. Similarly, in the, let's say, in the belt, in the first belt, the belt that was horizontal, we have calculated 7 2 by 2s. Now I want you to predict the same when I am doing it for the vertical belt. Vertical belt also we have gotten 7 2 by 2s. So in all, there are how many 2 by 2s? There are going to be 49, 7 into 7. Okay, I hope that is clear. 49 2 by 2s. And how many squares? Is it going to be 2 or is it going to be 4? That is the question. I just am curious. Obviously, it is not going to be 4, it is going to be 2. So 49 into 2, and the answer to this is going to be 98. Okay, so 98 is going to be the right answer to this question. Obviously, I have given you the idea straight up there, but then there can be a lot of things that you can do with this question itself. It's a very interesting question. The puzzle itself has been tested in some of the, other entrance exams, let's say, not pertaining to management. Okay, having said that, is this very difficult? You tell me, is this very difficult? Is this the kind of a puzzle that, suddenly blew your mind out of the picture? It's definitely not. This there is a way more elaborate textbookish method to this also, wherein you will go, at the corner how many squares I am getting, on the edges how many squares am I getting, inside of the chessboard how many squares am I getting. So there is a more elaborate textbook, this thing I'm there is this thing. If you Google, you can find. But again, the idea that I want to give you is that this is the most optimal way to solve this question. I hope you enjoyed something. If you did, please subscribe, and yeah, thank you.